Welcome everyone. My name is Michael Kelly. I'm an application engineer at Zoeller, and we appreciate you joining us for our Recirculating Media Filters overview webinar. Now, before we get started, I just want to cover a few details. Please note the email address written on the screen. Should you have any questions after we wrap up today, you can send them to webinars@zoeller.com. So again, that's webinars@zoeller.com, and we will get back to you. Now that those details are covered, I want to start off by telling you a little bit about myself. Again, my name is Michael Kelly. I graduated from Western Kentucky University with a Bachelor of Science in Mechanical Engineering and a Master's in Business Administration. I have been working as Zoeller's application engineer since February of 2018. I am a licensed professional engineer in the state of Kentucky. And during my time at Zoeller, I primarily work with customers, reps, and engineers with design and technical issues and applications including low pressure sewer, pump sizing, basin sizing, on-site water, wastewater treatment systems, and other specialty applications as well. But now that those details are out of the way and you know a little bit more about me, we're going to go ahead and get started with today's webinar. So again, we're talking about recirculating media filters today and just a general overview as to what they are, the components of them, how they operate, and a little bit about what Zoeller offers. And more specifically, the topics that we're going to cover is first, what is a recirculating media filter? Why would we use one? Why do we need to use this as a form of treatment for wastewater? We'll go through a quick overview of the treatment process. This will go all the way from the source of the waste to the disposal of that waste. And we'll spend some time on the media filter, which is kind of sandwiched in between of that treatment process, somewhere in the middle. We'll spend a little bit more time on that and the physical components and roughly how this system works. We'll talk about how we size a filter. So if you have a project that may benefit from a media filter, you have a general idea of how large this filter may need to be. Then we'll talk about maintenance. As with any treatment system, there is some maintenance required. Good news about media filters is the maintenance is relatively low when compared to other systems of equal size and capacity. And then at the end, we'll talk about what we at Zoeller offer both from a products perspective and a service perspective. So with that, we're going to go ahead and get in and talk about what is an RMF. So recirculating media filters, or commonly abbreviated as RMFs, is an aerobic fixed film wastewater treatment system that uses sand, gravel, or some other media to filter and treat effluent to secondary levels. RMFs are used to treat effluent from septic systems by recirculating the water through a treatment media. Media filters are essentially aerobic trickling filters where the wastewater is trickled over the treatment media and air is pulled in from the surface of the filter. Microorganisms will colonize on the surface of that treatment media, so around that gravel and around that sand, all around the surface area of that, you will get microorganisms that colonize on them and feed on the organic waste. So as that water trickles over that media, those microorganisms are eating away from that harmful waste in that water. RMFs are generally used to treat water to secondary treatment levels, which is taken in most cases to be 25 milligrams per liter BOD and 30 milligrams per liter TSS. BOD is being biochemical oxygen demand, which represents the oxygen demand to decompose organic matter. And TSS is total suspended solids, which, as the name implies, is a concentration of solids suspended in that water. So again, with a media filter, we're knocking this down to secondary treatment levels, being 25 milligrams per liter BOD and 30 milligrams per liter TSS. So why would we need to use a media filter? Why can't we just use a septic tank? Why can't we just, run a pipe out to a creek? First and foremost, but hopefully you don't want to just run a pipe straight out to a creek, but many times difficult soils can reduce the feasibility and density of a development. If you don't have good soils, you can you can't always treat that water on site with say a traditional septic system. Also, smaller lots are limited on the space available for a traditional septic system. So sometimes if you're going with traditional septic systems, you need a larger lot to get that system approved. Secondary treatment can also be used in rehab jobs to bring a failed dispersal system back to life. So if you have a septic system that has been deemed as failed, particularly the disposal field has failed, a lot of times if we clean up that water a little bit before disposing it, we can bring that disposal field back to life. So if you don't have a proper rehab area or an area set aside for a new disposal field, sometimes putting in a secondary treatment system can help bring that system back to life. Also, environmentally sensitive areas may have stricter discharge limits that, just a general septic tank cannot meet alone. So again, we want to treat that water a little bit more cleaner, so it's not as hard on the receiving environment. So let's take a residential development, for example. If approved soils are spotty throughout the proposed development, it may be difficult to get all lots approved, or it may require larger lots once you take into account setbacks and rehab area requirements and the potential for difficult soils at each lot. So the advantage of a media filter is we can collect and treat all the water in one area, which reduces the size requirement at each lot. So now we can get smaller lots, a denser development, and a lot of times developers like that, so they can get more lots and ultimately more revenue out of that piece of land. Communal treatment can increase the development feasibility by collecting and treating the water in an area with better soil. So if we have one particular area within the development that has better soils, then why not bring all the water there, treat it up, and then use those soils in that one central area. As well, also, when we treat the secondary levels, we're reducing the size of the dispersal field in many cases. And it also opens up options for other dispersal methods, such as drip, and then even in rare instances, we can use media filters on direct discharges. So again, this media filter allows us to increase the feasibility of developing a piece of land or rehabbing systems. So it's an added treatment beyond what just a septic tank can do by itself. So now we're going to transition. We've talked about what and why we would use a media filter. So now we're going to transition into just the general overview of the treatment system. And we're going to start at the source. And at the source, we're going to use a septic tank. So nothing special here, just if you're familiar with septic tanks at all, this is just a standard septic tank sized for the source of that waste. So for residential applications, you're usually talking to 100 to 150 gallons per day per bedroom, or commercial applications are sized as such, usually 2 to 3 times the daily flow of that application. But recirculating media filters treat effluent only, which is why we need these septic tanks. The media filters are not designed to treat raw wastewater. As you can imagine, the sand and that gravel have relatively small pores between them, so they do not handle excessive solids very well. So a septic tank is required prior to being treated by the recirculating media filter. The septic tanks will retain fats, oils, greases, and solids that would be problematic for the media filter. And in addition to that, septic tanks begin that treatment process, and they can generally treat domestic wastewater to about 50%. After the treatment system, we need to collect that water so that we can get it to the media filter. If we are treating a singular source of waste, the treatment is many times done on site. And therefore, the collection is primarily gravity. So if I have, say, an individual home or an individual commercial building that's using a media filter, we'll just put this recirculation tank in the media filter just immediately after the septic tank. But for communal collection, so say larger systems where we're collecting all that water in one area, we need some form of a collection system. So you could do septic tank effluent gravity, or commonly referred to as STEG, septic tank effluent gravity, STEG. You can use those. Though many times, and what I see most often due to the low upfront cost to developers, septic tank effluent pump systems or step systems are used for the collection system. We have a septic tank at each home or each source of that waste, maybe it being a commercial building in this system as well. There will be a septic tank with a pump inside that tank that can then pressurize that water into a force main, a small diameter force main that then collects all this water and sends it to the recirculating tank. If you want more information on pressure sewer collection systems, be sure to check out our LPS overview webinar on our YouTube channel. We did that just a few weeks ago, so it should be coming up on our YouTube channel any day now. So if you want more information on pressure sewer collection systems, be sure to check out our YouTube channel. But once we've collected that water, the first piece of the media filter that this water ultimately flows to is a recirculation tank, or it's really an equalization tank. Our media filters are timed dosed, so we do need to have enough capacity for those peak flows. So if you think of a residential application, you generally have a large peak in the mornings and in the afternoons. We're not going to immediately dose that water out as it comes in because this is a process-driven treatment system. We need to be able to store up those peaks. Most regulators, whether it be a state department, a county department, require 1 to 2 times the daily flow anytime you implement a time dose system. We do have some ways that we can reduce that requirement, and we'll talk a little bit about that as we get further into this, but generally as a rule of thumb, your EQ tank should be sized for 1 to 2 times the daily flow. So if I have a 2,000 gallon per day application, my tank storage needs to be around 4,000 gallons, 2 to 4,000 gallons. In this picture here on the left, you can see this is the inlet pipe here. The pump system, which we'll get to on the next slide, is over here on the far side. That is what is dosing this media filter. And then that water is being recycled and recirculated through the system. So it's a recirculation tank and an equalization tank. So for the pump system is generally comprised of a duplex or 2-pump system. Though more systems may be used for larger filters or new developments where construction will be phased out. For residential or light commercial, a simplex or single pump system is fine. Generally, I encourage people to go for duplex, especially if it's a commercial application or a communal application, just for that added redundancy. On larger systems, say it's a new construction or a new development for a residential neighborhood, where we will only be bringing on homes as they are built. In the early stages of that project, we're going to have very low flows to this media filter. And by bringing the entire filter online at once, we could starve the bacteria within that media filter. So a lot of times what we'll do is we'll put in individual pump stages or pump systems as we reach different stages within the project. So for instance, if we have a 100 lot development, maybe we'll break our media filter up into 4 zones, where from the construction phase where we're between 0 and 25 homes, we just have 1 pump system feeding 1/4 of our media filter. And then once we get to the 26 to 50 homes, we bring in that next pump system to dose the other half, or the other quarter rather, of that media filter. And we can stage that out in line with the construction. Now, as far as the pumps go, we can use step pumps, so septic tank effluent pumps, or step systems, where generally that's referring to a turbine effluent pump similar to well pumps, if you've seen those before, or our traditional centrifugal pumps that Zoeller is very well known for. We generally put them on rail systems, as you see here. I do recommend that we use pressure filters on the discharges of these pumps. If you're using a step system, there's filters before the pump in that case, so the need for a pressure filter is reduced. But if we are using, say, a standard centrifugal, as shown in this drawing here on the right, I would recommend a pressure filter on the discharge of the pump. And you can see that here. This is the pressure filter here, and that's to to protect the distribution system downstream of this pump to prevent any solids from getting out and potentially plugging that. So now we've gotten the EQ tank is part of the media filter process, but the actual physical media filter, to break that down, it's really easy to break this down into 3 zones. Starting from the top, this 6 to 12 inch layer here that you can see kind of cut away with the lighter gravel on top, that is the distribution zone. This is what's going to house the laterals and the orifices and the orifice shields. This is where we're pressurizing these laterals to evenly distribute that water throughout the media filter. Going down beneath that, the next zone is the treatment zone. Generally 24 inch minimum, and that's usually our standard is 24 inches in depth. You can go deeper to maybe get a little bit more treatment, but usually 24 inches is adequate. And this is usually going to be sand or gravel in most cases. Going down below that is the collection. So this is where we're collecting the water to either recirculate it back through the system or to send it out for final disposal. And we can use chambers, or commonly used also is slotted 4-inch pipe to collect that water. So look a little bit more closely at the distribution system. I've got 2 pictures here, and you can see that the distribution system is essentially an LPP system with evenly spaced laterals and orifices. The pumps are sized to provide 3 to 5 feet of distal pressure at the flow required per the size and number of orifices. So if you're familiar with mound systems, or if you're familiar with LPP, LPD, low pressure distribution systems, this is essentially the same thing. It is the same thing, where we're pressurizing small diameter laterals with evenly spaced orifices. And our hope is to get 3 to 5 feet of pressure on each one of these orifices so that we can ensure even distribution across this entire filter. In most cases, even on our smaller residential systems, we use mechanical indexing valves to break up the distribution system. This usually allows for more economical pumps, and it also increases rest periods for different zones. So you can see this filter here on the left is broken up into sections of 3 laterals. You've got various stub outs. On here on the right, this is that same filter system, and we've got 3 different multi-zone valves here. So these indexing valves, we call them multi-zone valves in our literature and marketing. These indexing valves will alternate between zones. Each one of these valves is hooked up to 5 different zones. So cycle number 1, we'll go out to zone 1. Cycle 2, we'll go to zone 2, 3, 4, 5, and then back to zone 1. So indexing through those valves allows us to make sure we're evenly distributing water across the entire filter. We're increasing the rest time for these filters, so we're not getting any particle wash through. We're benefiting the colonization of that bacteria by doing this. And it allows you to get away with smaller pump systems. And I talked earlier about phasing out systems with multiple pump systems. This is a good example of that, because each one of these 3 multi-zone valves is linked to an individual pump system. So since this was a new development, whenever the first home was built, we probably just had 1 zone online. As more homes were built, as we reached the second third of that development, we brought on the 2nd zone. And as we approached full build out, we pulled on all 3 zones. So again, we're kind of building this system out as the construction is phased out. So the treatment media is next. So again, we're moving our way down through the filter, kind of as we discussed earlier, but the treatment media should be a minimum of 24 inches in depth. You can go a little bit deeper, though again, our general standard is just to go with that 24 inches. Sand and gravel are the 2 most common medias, though other medias do exist, such as glass chips, tire chips, crushed brick. There's other things out there, but since sand and gravel is usually the most readily available and easily accessible media filter, it's generally the most commonly used. Our general recommendation is to use 1/4 to 3/8 inch washed pea gravel, which you can see here in this picture on the right. This is the media from one of our treatment systems that we install. Sand will generally treat better than gravel. The treatment is somewhat correlated to the pore size, so sand being smaller than gravel has a larger surface area. The larger surface area allows for a larger colonization of bacteria. And that larger colonization of bacteria then treats the water a little bit better. However, the primary drawback of using sand is it becomes very susceptible to plugging and ponding effluent. And when that happens, many times it requires that media to be replaced, which is a very costly and potentially hazardous job to do. Alternatively, using gravel, which is becoming more and more common across, the entire country. Most of the jobs that I see, even before giving our pitch for gravel, they're generally requesting gravel up front. So I know it's becoming more and more common, but the primary benefit is the reduction in the chances for the system plugging. So to my knowledge, we've never had one of our gravel filters plug, and we've been doing this for many, many years. The larger media size also still gets adequate treatment. So since we're still able to hit well within those secondary treatment levels, reduce the chances of plugging, gravel tends to be the preferred option for most applications. So now we'll talk about the collection. So after it's been distributed across the filter, after it's trickled down through the media, the treatment media, now it's coming into the collection area. And as I mentioned before, we really got two options. We can use chambers or we can use slotted pipes. So you can see here on the left, we've just got 4-inch, I believe it's SDR 36 PVC pipe that's slotted. This, as the water gets down in here, will find its way into the pipes, and those pipes will take it back to the recirculation tank or out for disposal. Around this pipe, we're usually using 3/4 to 1-inch gravel. So slightly larger gravel, it's usually more readily available. We're not really using this gravel for treatment, so the larger diameter is less of a concern. But it also helps keep gravel out of the collection system, so we don't have any small pieces of gravel washing into this collection system here on the bottom. On the right, we're using chambers. So chambers naturally cost more, so why would you want to use chambers? The advantage of chambers is many times we can use that volume within those chambers to reduce our tank requirement. So we talked earlier on the recirculation tank that generally it needs to be sized for 1 to 2 times the daily flow. If you're treating thousands, if not tens of thousands of gallons, that can become a rather large storage requirement. We're already using this area for the treatment, so why not use some of that area for some storage? So using the void space within these chambers, as well as the void space within the gravel, we can increase our storage footprint without increasing the real estate needed for this treatment system. So after we've trickled that water through the filter and we've collected it in the bottom of the filter, we need to recirculate that. Ultimately, we also need to be sending some out for the disposal, or else we'll just be continually recirculating water. So the typical recirculation rate for media filters is 80-20, with 80% returning to the recirculation tank to be dosed through the filter again, and 20% going out for disposal. There are multiple ways to set the recirculation rate for media filters. You can use fixed walls, you can use D-boxes, orifices, and there's other methods out there that exist. The two we most commonly use are going to be fixed walls and a weir plate that we refer to as a cat's eye weir. The fixed wall is typically installed to divide the filter 80-20. So you can see here on the left, we've got this fixed wall that runs the length of this filter, where 80% of the surface area is here on the right, 20% is here on the left. So if this is a 50-foot long, or 50-foot wide rather, media filter, this wall is at about 40 feet. 40 feet being on the right, 20 feet being on the left. So that Any water that falls and trickles down on this right side will be recirculated back to the recirculation tank. All water that falls on the left side will go out for disposal. And an 80-20 recirculation rate generally means that each particle of water will pass through this system on average 5 times. Every time it's getting a little bit cleaner and a little bit cleaner. So that's what helps us really get this water cleaned up really well with relatively simple technology. On the right, we've got what, again, we refer to as a cat's eye weir. You can see it's just a T here. The media filter is here at the top of the picture. The water is collected, flows through this pipe into this T. You'll notice there's a little black handle here. That is the weir plate. And it's called a cat's eye weir because the 80-20 weir looks like a cat's eye. The advantage of this method is this weir plate can be changed. So if you want to increase your recirculation rate, maybe to a 90-10, you can do so. If you want to decrease it, maybe to 70-30, you can do that as well. That can be advantageous. So you can have a little bit better control over the treatment of the system. But the way that it works, it'll flow into this T. This weir specifically cut so that 20% will go out here to the right, which will go out for disposal. 80% will come back to the tank, and you can see kind of the top of the tank here. So this is coming back to the recirculation tank to be recycled through the filter again. So the fixed wall, the primary drawback of that is you have no variability with this. Though usually we're using these on larger commercial communal type treatments where we're usually getting a pretty predictable waste strength where, you know, the need to alter that recirculation rate is very minimal. And this is usually our standard for the larger systems, and, you know, very routinely are we hitting well within secondary treatment levels. So after it's been treated, it goes out for the disposal. So generally effluent from media filters is disposed subsurface through conventional trenches, low pressure pipe, or drip systems. You can also do mound systems, which this particular job had a mound system. You can see they've got the gravel laid out with the piping and the dirt and sand on site to build up the mound. So this particular application used a mound system for disposal. And though less common, media filters can be used for direct discharge. If you are going to do that, it does need to be disinfected or sterilized. We generally do that with chlorine or UV. You could use peracetic acid, though that's fairly uncommon, kind of on the on-site decentralized systems. That's more for municipal applications. But if you ever do a direct discharge, you always need to disinfect or sterilize the bacteria that remains within that water. So now we've gone through the treatment process and the treatment overview. Let's talk about how big do these filters need to be? How do we know to size these systems? And there are 2 things to consider when sizing a media filter. The first is hydraulic loading. The second is organic loading. So hydraulic loading refers to the total gallons per day to be treated by the media filter. So if I have 10 homes at 300 gallons per day, my hydraulic loading is going to be 3,000 gallons per day. And to break that down into a smaller number to size this filter, we've got these 2 values here. Generally for gravel, we're looking at 5 to 15 gallons per day per square foot in that media filter. So we're generally trying to calculate the total area of this system. For gravel, we generally recommend a design value of 5 gallons per day per square foot. That's a little bit more on the conservative side, but that will generally cover you for most all applications, including the organic loading, which we'll get to here in a minute. For sand, since it has a smaller pore size, it needs to be loaded less heavily, 3 to 5 gallons per day. On here, I've got a design value of 4 gallons per day. I would really probably encourage people to go to the lower side at 3 gallons per day per square foot. On the organic loading, what we're looking at is the pounds of BOD, the biochemical oxygen demand, the organic loading that's this filter, the waste strength, if you will, that this filter will need to treat. For gravel, really anywhere from 2 thousandths up to 15 thousandths pounds of BOD per square foot. For a design value, I would recommend 8 thousandths pound per square foot, or that equates to 8 pounds for every 1,000 square feet. Sand, on the other hand, again, since it has finer pores, you don't want to load that as heavily. So an acceptable range for sand is generally 2 thousandths up to 8 thousandths pounds of BOD per square foot. Design value being 5 thousandths BOD per square foot. I throw these out there with caution. Different sources provide different values for both. Generally, we recommend 5 gallons per day per square foot on the hydraulic loading. That's where we start. And in most cases, that's going to cover you on the organic loading from a gravel perspective, at least. So we recommend gravel. We recommend 5 gallons per day per square foot, but you want to check that organic loading as well, just to ensure that you're not overloading from that perspective. Though for most domestic waste drinks, the 5 gallons per day per square foot is going to be far sufficient. But if you're anticipating higher strength waste, be sure to check the organic loading as well. But as I mentioned, the different sources provide different values. So if you're working on a project, I would start first with whoever regulates the system, whether it be your county health department, your state health department, or the environmental resources department. Whatever department oversees these types of systems, reach out to them and see if they have any design standards on how to size these systems and use that, because ultimately they're going to be the ones approving this. It doesn't matter what I say, you should size these systems for. If they have their own set standards, you should follow theirs. This is just to give a general idea of what we typically do and what we typically recommend when sizing these filters. And as you're looking at both of these, ultimately, in most cases, you're going to end up with 2 different area requirements. So use the more conservative value. So whether the hydraulic loading or the organic loading, whichever produces the higher total square feet required, use that value. So we'll do a quick example. Let's say we've got 5,000 gallons per day. Our design BOD is 150 milligrams per liter. So again, we'll start first with the hydraulic loading. And again, to calculate that area, all you need to do is take the total daily design flow and divide that by your loading rate. So with 5,000 gallons per day and a design load rate of 5 gallons per day per square foot, we would need a filter that's 1,000 square feet or larger. But it's always good to check the organic loading. So we are given a concentration of 150 milligrams per liter. If you recall from the slides earlier, I was talking about pounds per square foot. So we need to convert that concentration to pounds. And there's an equation out there called the mass loading equation that takes your concentration of milligrams per liter or parts per million, multiplies that by the daily flow rate in million gallons per day, and then multiplied by a conversion factor of 8.34. So in this case, we have 150 milligrams per liter. That's our design organic loading or concentration, multiplied by 5 thousandths of a million, which is equivalent to 5,000 gallons per day. And then multiply it by the conversion factor of 8.34, we get a total of 6.25 pounds of BOD per day. So now that we know what our organic loading is, we can divide that by our load rate and calculate the area required. So taking 6.25 pounds BOD, dividing that by our loading rate of 8 thousandths pound per square foot, gives a total area requirement of 782 square feet. Though if you remember from the last slide, when we sized for the hydraulic loading based on 5 gallons per day per square foot, it required 1,000 square feet. So in this case, the filter should be a minimum 1,000 square feet in size. And that can be a 30-foot wide by 33-foot long filter, or a 50-foot long by 20-foot wide filter, whatever the layout. Most of our larger systems are in 30-foot and 50-foot lengths, and then, or widths rather, and then the lengths will vary based on the area required. Maintenance. So the great news, all on-site systems require some form of maintenance. The good news about recirculating media filters, it requires very little maintenance, especially when compared to alternative treatment systems of the same capacity. Potentially thousands or tens of thousands of gallons may be flowing through these, and you really only need to maintain these every 6 months. Though I will say after startup, so when you first install this system, the filter should be checked on periodically to ensure it is operating as intended. So for the first week, maybe go out a couple times to check, make sure there's no alarms, make sure it's operating as intended. And then after that, maybe once a week for a month or two. And if after a month or two, if you've kind of confirmed that, nothing adverse is happening, it's operating as it should, because whenever you install these systems, the floats could be set wrong, the timers could be set wrong. There's a few things that could need fine tuning in the beginning. But once it's been proven to be reliably operating, you really only need to check on the system every 6 months. And during that 6-month maintenance period, you want to inspect the control panel for moisture, gas, or corrosion. And in any on-site application, anytime you open up a control panel, you want to take note of the smell if there is any smell. If you could smell that rotten egg, sulfur smell, you need to seal your conduits. That gas becomes very corrosive and can actually fail your control panel. So if you notice when you open a control panel and you smell that rotten egg smell, make sure you go back and seal your conduits, both in the pit and at the control panel. That double seal will give you the best protection. You want to test the alarm of floats for proper operation. So you'll just be flipping the floats up and down and make sure you're getting the proper response from the system. You'll check your running amps and your voltages for all pumps. And then you want to also check run times and cycle times for each pump. And it's good to keep a log for these. And our O&M manuals will include that log. But you want to log your amps, your voltages, your run times, and your cycles for each pump. That will kind of give you some historical data. So maybe you can notice maybe some trends that may be occurring over time that may need to be addressed. And if you can, check your alarm counts. So some of the panels we have will give you your alarm count, so you want to check those as well and maybe log those. You want to remove, inspect, and clean the pumps. So pull them out, spray them off, and they may get some sludge or grime built up on them. So you want to clean them up, make sure they're operating as intended. You want to check the recirculation tank for sludge accumulation. So granted, this is post septic tanks. We shouldn't see a lot of sludge buildup in these systems. But if you do start to get some accumulation, depending on how that system is set up, maybe around 12 inches or so on the bottom of it, you're going to want to pump out and clean that tank. Inspect all the filters in the recirculation tank. So we talked about filters within the pump system earlier. So step systems are going to have a filter bank inside of that step vault. So you want to pull those out and clean those off. If you have a pressure effluent filter, so we talked about if you have just a standard centrifugal pump, a pressure effluent filter on the discharge of the pump, you want to pull that and clean it and reinstall all of those, of course, and then pull the weeds that may have grown in the filter. And I say pull the weeds. You do not want to spray or burn the weeds. Spraying the chemicals within that could be harmful to the bacteria in the media filter and reduce treatment levels. Burning the weeds could lead to plugging. Spraying could as well, because you're not removing that root wad. A lot of that's dying and decomposing there on top, which just puts additional solids into the filter that don't need to be there. So anytime you see weeds, just pull them out and throw them off to the side. Don't lay them on top of the filter and leave them there either. Pull them up and remove them. You want to check the multi-zone valves for proper actuation and operation. This is pretty easy to do. You can have somebody stand out in the filter, turn a pump on, and you can hear the zone that's active. And you'll turn the pump off, turn it back on, and make sure that it's indexing to a different zone. If not, you'll want to go and pop the top off on the multi-zone valves. Very easy to do, just a few screws, pop them off, make sure there's no debris that may be catching that indexing valve. You want to flush the lateral. So this picture here on the right shows this being done. This is done at startup when this picture was taken, but it should be done periodically to make sure you don't have any bioslimes building up inside of these or plugging any of your orifices. So each one of the laterals will have a clean out with a threaded cap on the end. So you'll just take those caps off, turn all the pumps on in hand to get as much water flowing through the system, open any ball valves between the pumps and these laterals to try and get as much flow through them and scour them as best you can. If it's been a while, sometimes you'll see kind of a dark gray or black slug get pushed out of these systems. So just run the pumps until that water starts to clear up, turn them off, put the caps back on. And then after you flush your laterals, you'll want to recalibrate. So we talked about we want to have a distal pressure between 3 to 5 feet. You don't really want any less. You don't really want a whole lot more. So with each of the filters, you'll actually get this calibration tool that you can kind of see laid in this picture here. It's a clear piece of pipe with a female threaded connection on the end. You'll actually thread that down onto one of these laterals. All the others will be capped. And then you'll turn the pumps on. And there's 2 marks on this clear tube at 3 and 5 feet of pressure. And you'll just want to run the pumps, make sure it's between those 2 lines. If it's too much flow, if it's going above the top line, you'll use a ball valve to kind of turn back that pressure in that system to kind of choke down the flow a little bit. So once you've recalibrated it, ensured the controls and everything else are operating as they should, you're good for another 6 months. And I also want to state that these systems are very resilient. It's unfortunate, but in the on-site market, maintenance is it's very much an afterthought. Most people are reacting to failed systems rather than maintaining their perfectly operating systems. It's usually not until something has gone wrong that people are going out to check on the system. The good news, these systems are very, very resilient. We've been out on job sites where these systems have been neglected for years, and within a half day's work, had them back up and running as if they were just installed. So if you go through the list that we just discussed, even if it's been years before the system has been maintained, a couple of people out there could knock it out in 4 to 6 hours and have that system back up and running. Short of having to replace pumps and having the appropriate spares on hand, but very quick to bring back to life. So now we're going to transition into what Zoeller offers, and we'll first start with the product side of things. So Zoeller is most commonly known for their pumps. So we can of course offer the pumps, the rails, the controls, the check valves, ball valves, indexing valves, etc. We have all of those. So it's what we're most known for. But we also have media filter kits. So these can be easily installed in the field with all the components you will need. You don't have to go out and try to source all these or try to get your quantities just right. We do all that for you. We've got these kits that we've already got set up and have been building for years. The kits include the EPDM liner. So this is going to be this black material here at the bottom. We do use a 45 mil EPDM material. Some other people out there have used PVC. PVC is okay when it's first installed. The issue is it becomes brittle over time. And when it becomes brittle, it becomes susceptible to cracking. And you don't want this water leaking out here. You want it to stay contained within the system and only exit through the collection system. You don't want it leaching out the sides of this. We also have a protective underlay mat for that liner. So this lighter gray here at the bottom represents that underlay. That's just to protect that liner from any rocks or sharp objects that may not have been properly excavated during the installation. The distribution and collection piping, including the cleanouts, risers, orifice shields, and penetration boots, are all included. So all of these laterals are pre-drilled with the orifice shields, the cleanouts on the ends, these risers for the chambers or the slotted collection pipe, whichever one you may be using for your project. All of the chambers, all the plumbing to connect them all will include about a 24 to 36 inch stub out for each one of the penetrations through the wall. So this collection system will ultimately stub out through the wall. We'll have about a 36 inch pipe to get you outside of that wall as well on the lateral assemblies. So everything within this filter from a plumbing perspective and the liners is included. We also have a safety fence that we include. Now the safety fence is not to be used around the filter. It's actually laid within the distribution zone. So you'll put in your laterals and then you'll roll out this safety fence just above those. And that's basically a deterrent to keep people from going in there and digging it up. In case, somebody wanders in there and thinks it's a play pit or something, start grabbing in it or digging in it, hopefully that orange safety fence will stop them from doing so. Items provided by others would be installation, so we do not install these. The gravel will be supplied by others from a local source, ideally. The filter media, which is also usually gravel. The tanks for the recirculation tank would be supplied by others, and the lumber on this frame that we build around it would be supplied by others. Speaking about the frame, this is really just a 4-foot wall, so we haven't talked about the depth of these systems. These are generally 4 feet deep, so you'll build a 4-foot frame around it, and that's what the EPDM liner is draped over to create this watertight basin, essentially. People can use concrete. It's like building a swimming pool. It's just usually a little more costly and a bit more labor intensive as well. So we've had a lot of success just building a 2x4 wall with some plywood. You have a 2x6 that goes around to cap it off to nail down that EPDM liner. But pretty simple and easy to install in the field. From a service perspective, we provide free technical assistance. So this is at no cost to you. We provide scaled AutoCAD drawings that are custom to your project as needed. We have a rather large library of different filter systems, but if there's something custom that we need to do to meet your local regulations, we can draw that up for you. And this could be used for your permitting, your construction, or as needed. And we can provide those drawings for you. System sizing, so we'll help you size not only the media filter, but the pump system. We can also do the pressure sewer analysis. So we talked a little bit about collection and using step pressure sewer system. We can help you size that collection system as well, in addition to the pumps that will be used at each home or at each connection point. We have specifications for all of the equipment. We also help with the selection of the equipment. So we'll help you with your quantities and your takeoffs for these systems. And then lastly, training and support in the field. So we will come out, we can help you evaluate sites. We can come out for pre-construction meetings. We can come out and meet the regulators, whether it be the health department or the state department. We can come out and meet them. We've done virtual meetings with regulators before to kind of help push these systems through on approval. And of course, we'll help with support in the field. So we will help train up whoever's going to maintain the system, or train the owner if they're going to be maintaining that. So all of that, again, is free. We just hope that if we do all that for you, you will use our equipment for that project and projects in the future. So if you have a project in mind, reach out to us and we'll help work with you through that project to get that system approved and to get that system installed. But this concludes the presentation portion of our webinar. We've uploaded some handouts regarding the information presented here today. They include 2 catalogs. One is for our environmental products, and another is for our decentralized wastewater treatment systems. Additionally, there are a couple pieces on our recirculating media filters and our turbine step vaults, which we've talked a little bit about today. So please be sure to check those out and download a copy for yourself before you leave today. Should you think you have lingering questions, again, please jot down our webinars email and send them our way. So that's going to be webinars@zoeller.com. Again, there on your page right there. So be sure to jot that down. And with that, we'll wrap things up. Thank you all so much for taking the time to join us today. Have a great rest of your day.